5, 4, 3, 2.
So everybody, you may have recognized that from a show that, well, Miss Dolly loved watching. She doesn't watch it too much anymore. We'll discuss it sometimes if you think you know where that came from. All right, we're going to start a new unit here, and that's our Unit 2, which primarily comes from some Chapter 3 sections of 3.7, 3.8, 3.9, 3.10, some function evaluation, which is scattered throughout the unit. It's scattered within this unit, and then I throw some graphing function evaluation in there. Then some domain and range, which I also scattered throughout the unit. Then there is a new section I have to add to this. So after section 3.7, 3.8, 3.9, 3.10, we'll call the next one 3 point golly. Called sections that before, where we are going to work on piecewise functions. The function evaluation and the domain and range are topics that are found within these sections, and the piecewise function is found on page 95 on this packet. So I haven't decided if I'm going to do it as its own little mini unit on page 95. In the past I have, but the way that the classes are, all block scheduling right now, that might take a little too long to do, so I might incorporate it into the whole entire unit too. So what you're going to have is notes that you're going to take right now, and then a homework that's going to be assigned, and I'll tell you which notes to upload. Normally I start with section 3.7, but I'm not, because that's something I really need to teach you in person. So I will be teaching you section 3.8. I usually break it up into 2 days, but being block scheduling, this will be a 1-day section. So I'll tell you which pages of these to upload. Then these will be our sections afterwards. So let us start on page, wherever 3.8 is. Because remember, I'm not doing 3.7 right now. I'm going to, but not yet. So 3.8 starts on page 15 of your yellow packet. So here is your yellow packet. And today's objective is to find the values of functions and to graph functions. If at any time I'm going too fast for you, all you have to do is pause your video. So functions is such a big idea in the world of algebra. So you kind of need to know what a function is before you start doing a bunch of things with functions. You're going to graph functions, evaluate functions, evaluate functions. Did I say that already? Create functions. And there are going to be all type of functions. Linears, quadratics. We're going to primarily deal with linear functions. So we have to know what a function is. So according to the definition, this is the thing that makes people know what functions are or less, but I'll give you the definition, of which you never have to really repeat it exactly back to me word for word, except when I say, is this a function? A function is a correspondence, which is, just like a relationship. Between two sets. These two sets are called the domain and the range. That assigns like this. For every input, there is exactly one output. You can't say for each input there's an output, because it's not like each input gets an output and more and more and more outputs. It only has exactly one output. And when I'm talking about the domain is all the inputs, while the range is all the outputs. Right there. So, and I'll define that down here too. So if you're in my Algebra 1 class, you've probably seen me do a section just like it because I just kind of cut and pasted this for my Algebra 1 class so I could do a little review of what a function is. You've seen functions in different representations. Here are the representations. Mapping diagrams, which it'll be, at first you'll be like, wow, this is a lot of listing. How am I going to remember this all? Because after I list mapping diagrams, see, I'm going to show you mapping diagrams. The next one is going to be tables. See, the next one is going to be ordered pairs. The next one are going to be scatter plots. So when I list all 7, I show you all 7 in the coming pages. So tables, ordered pairs. These are all ways to represent a function. Scatter plots, graphs, which scatter plots are a subcategory of graphs. Equations, that's the biggie, really. Creating your equation, using your equation. Sometimes we call that the rule, and sometimes you see it as a formula. You are now have to create your own rules and formulas and equations. It's not Algebra 1 where it's given to you. And words. So those are the 7 ways that you represent functions. When I show you these 7 ways, you're going to also have to learn to go between the 2 ways. They all overlap. And you learn to make one table into an equation or an equation into words. So here's an example. Here's a table, and the table is XY table, and it's 0, 0, 1, 2, 2, 4. Could you create an equation from that? So can you take this table and turn it into an equation? So you notice that it's doubling, so you just call it y equals 2x. So now you've created the rule for that table. Can I give you words, like a word problem? Sure, I'll show you a word problem I'm going to give you. And these are words right here. And in that word problem, I'm going to say, I would like you to make the equation from these words. And after you make that equation, I would like you to make the table for these words. So the words to the equation to the table. So you're going to be going between all 7 of these. Okay, so the first of these is the mapping diagram. In the mapping diagram, you see that these guys all over here will be your inputs. These guys will be your outputs. So, why is it called a mapping diagram? Because the first input of -8 is mapping onto -6. -8 also maps onto 1, the output. -5 maps onto 2. 7 maps onto 3. And the question is, why is this one not a function? So that's probably something I haven't shown you yet. I mean, if you've been in Algebra 1, you should know this, and you've all been in Algebra 1, so you know this. The reason it's not a function. By the way, it's a relation. You probably haven't heard that word before. Everything is a relation because it has a relationship. But is this relation a function? So go back to the definition, which it says each input has exactly 1 output. So I'll ask you this question. How many outputs does 7 have? It has 1. So far so good. How many outputs does -5 have? It has 1. So far so good. How many outputs does -8 have? Yikes, it has 2. So the answer is this is not a function, and if someone asks you for a reason, you'd say because the input of -8 does not have exactly 1 output. It has 2 outputs. See that? So let's take a look over here at this relation. Well, it's a relation because Z is a relationship. And right now, this is the ordered pair form of it. You could block it out. It doesn't matter. They all overlap, so I don't mind that I showed you that first. This is how you represent it as ordered pairs. So now you take the x value of the ordered pair, 1, 5, and 8, and put it on the input side. And then 1 matches with the C. 5 matches with the A, 8 maps onto the B. It shows you right here. This relation is a function. We say yes, it is, because for each input, there is exactly 1 output. So that one is a function. So notice how I took these ordered pairs and I put them into a mapping diagram. Again, you can go between all of them. If I were to take this and turn this into a table, I know I'm being a little premature here, but it's so easy. I mean, you've seen functions so many times before. So if I wanted to make a table out of that, I'd make it an XY table, and I'd put -8, and I'd have to list -8 twice. Notice in the mapping diagram it gets listed once. You don't list it twice or you actually will be marked wrong. So -8 maps onto -6 and onto 1, so that's the ordered pair it would be. -5 maps onto 2 and 7 maps onto 3. If someone asked you to even put this in an ordered pair version, you would just list these ordered pairs. So when you want to know what the domain is, the domain is the set of all the input values. The domain is not the input, it's all the input values. So in this one right here, if I asked you for the domain, it would be like this in the solution brackets, 1, 5, and 8. The range then would be the set of all the output values. Which in this case would be A, B, and C. And don't list it twice. So we only went over one of the types of functions, but really we did a lot of them, I think, over there. Let's take a look at the next one, the tables, as a representation of functions. So the tables is the second type that I'm talking about. So the question is, in this table, would you say that if these are functions or not? So let's take a look at them. I have 2. If you were to doing it as a mapping diagram, you would say 2 maps onto -16, 3 maps onto -24, and 5 maps onto -40. The answer is yes. The domain, and I didn't ask you why, but you could know why. Just repeat the definition. For each input, there is exactly 1 output. So, I mean, you could write it. For each input, there is exactly 1 output. So the domain, you put the squigglies, and you write 2, 3, 5. The range is -16, -24, -40. If I were to go ahead, of myself, would you be able to make this into an equation? It's just another form of the exact same function. And that function would be y is equal to, is it -8x? And I will be asking that soon, just not yet. So is this one a function? Take a look. The answer should be no, because notice the input of 2 has 3 outputs. You need exactly 1. So the domain is only 2. Don't write it more than 1 time. The range is -16, -24, -40. Now, how do you write the equation of all these? That's when you did the slope-intercept form. Remember, you found the slope, you found the y-intercept. You did that in your prerequisite test. But this one right here is just, you can eye it and look at it and say, oh, it's just multiplying it by -8. And some of them are not obvious. Like this one is not an obvious one, so I wouldn't be asking you for that one. If you ask for the equation of this one, it's a tougher one to remember how to do. It's just x equals 2. Not the value x equals 2, the equation. So ordered pairs is the next kind. And when you see the ordered pairs, you usually see it with these solution brackets. Is it a function? Let's see. 5 maps onto 4, 3 maps onto 1, 5 maps onto 0, and 2 maps onto 7. So the answer is no. If you made a mapping diagram of it, maybe a teacher wouldn't even ask you to. Maybe you can see that in your head. And the reason is the input of 5 has 2 outputs. The domain, you list it once, 5, 3, 2. You usually do it in order, but sometimes the equations are so different and the inputs are so different, you can't force yourself to do it. And there's your range. So that's the third thing. Now, I don't think you have this at the bottom of your page. I kind of wanted it at the top of your page, but there's not a lot of room. So I'm going to show you something called scatter plots for a second before you look at the definition of this thing called the vertical line test. I'm going to show you the next thing called scatter plots. Scatter plots, you could find out if something is a function from the scatter plot by actually looking at these ordered pairs and just say, oh, I think I just could list all these ordered pairs. That one looks like -1, 0, 1, 1, 2, 1, I think. And then it's hard for me to see this. 1, 2, 3, 4, 5, 6, 3. And you can say to yourself, hey, this one is a function, because for each input there's exactly one output. But once you start listing this one, you say it's 0, 2, 0, 3, and right now you know right away it doesn't, because the input of 0 has 2 outputs, 1, 2, 3, 4. So it's 4, it looks like 4, 4, and then 4, 5, 6, 7, 7, 5 maybe. If I'm wrong, big deal on it. So the answer to this is no, it's not a function. So it really is a hassle listing. You don't really want to list this. You want to do what's called a vertical line test to find out if something's a function. And here's how the vertical line test works, and then I'll define it. I get myself a piece of spaghetti. Oh, don't do this at home. Could get dangerous. You could hurt your little brother. But anyway, you take a piece of spaghetti, or you take yourself a visual, and the vertical line test says, not horizontal, vertical, if I only go through it once. See that right there? I only went through it once. I only went through it once. I only went through it once. And I only went through it once. So this tells me that it's a function. And I'll show you the definition in just a second. Here it is. Right at the bottom of the page. I call it VLT. VLT is a vertical line test. It's a test to determine if a relation is a function. That's its definition. What's its procedure? What is the procedure for a vertical line test? What do? You get out a piece of spaghetti and you do this first, because it's really fun. And then after you get out the spaghetti, you check if the vertical line goes through the graph. And when I do air quotes for graph, because it could be a picture of anything, like what's your graph? Is it a line? Is it scatter plots? More than once. So if the vertical line goes through the graph more than once, then the relation is not a function. Not a function. So let's take a look at that now on the next page. I actually rewrote this at the top for you. So the vertical line test, it's the same thing I wrote at the bottom for you. And we're going to look at scatter plots. Okay? Now, I listed those right over there. I listed them, but it's a hassle. It's too much work. Make yourself do a vertical line test. One time, one time, one time, one time. So this absolutely is a function. And this one, oh, one time. Oh yeah, one time. Whoopsie, that's 2 times. That's why this one is not a function. See, that it's pretty easy to determine with a vertical line test if something's a function or not. You wonder why we even learn something so easy, but we learn it because it's a shortcut to why should I have to list those ordered pairs? Why should I have to list those ordered pairs? See, when I could just tell by putting a spaghetti through it or a mental spaghetti in your head. Same for this one. It goes through it once, 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 once. But this one is twice, so it's not. Once and once. So this one is a function, once, 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 once. This one, all of a sudden it's twice. I don't care that those are once. This one's not a function. So is and not. You do the same thing with the graphs. You use the vertical line test. By the way, the vertical line test comes back at the end of the year again when we're doing something called inverses. So graphs, scatter plots are examples of graphs. You can put them in the same category, I guess, but a scatter or plot is a specific graph. So I told you we were gonna do one of each kind. We're probably on the fifth one, I think. So graphs is the fifth one. Take your spaghetti, goes through it once each time, see? Goes through it once each time. And goes through it once each time. Now this one's just a bad drawing because it looks like it's going straight up. This is what it's just my bad computer really giving me a bad parabola. But right there, these are all examples of, yes, these are functions because this vertical line goes through one time, and one time. See that? These are not functions because look, even though this goes through only one time right there, it's only once. Once it goes through more than once, it's all over. This is not. This is not, even though it goes through once there, it goes through twice here. And a lot of people get this wrong, but a vertical line is not a function because once you put a vertical line through a vertical line, it goes through an infinite amount of times. See that right there? So maybe you used a spaghetti at home to do it. Maybe you did not. But either way, you could do a mental spaghetti in your head. Okay, so I think we're on the fifth one. And the fifth one is rule. Rule. Rule, you could say maybe equate. It's right here too, also equations. Rules. Formula. All the same type of thing. So when someone says function, you're like, well, what kind of function are you representing? Oh, it's a table. Oh, what kind of function are you representing? You ask the next teacher. Oh, I'm doing it with equations. So, but you can represent it for your teachers at all. You know, the teachers can represent it for you at all different times in different ways. So sometimes they can't actually get the rule to something. So obviously you might have to do slope-intercept form. And I think we'll have to do that for the last one. So let's take a look at these tables that I'm going to turn into rules. So notice, how do you get from -1 to y? Oh, by the way, you know how we call things x and y? And we call a rule y? Well, we're going to call this one f of x. We've got to start getting used to f of x. So this rule is I'm just doubling it. So normally you would write y equals 2x. This time we're writing it as f of x equals 2x. And in this case, the domain listed is -1, 0, 1, and 2. And the range listed is -2, 0, 2, and 4. So you can also make an equation from a mapping diagram. It's just the one that the teacher asks you to make it from. Could you make it from a line, a graph too? Sure. If a teacher gave you this, you could make an equation from this. Make equation from it. You did in your pretest of your prerequisite skills. Make an equation from a line. Why couldn't you? Of course you can. So this one is when multiplying by -2. I don't know if you saw it. These two are the obvious ones, and this one's not as obvious. So you have to go back to your idea of slope-intercept form, where you find the slope, right? Where you do y sub 2 minus y sub 1 over x sub 2 minus x sub 1. You pick any two. Maybe I'll just randomly pick these two right here. And I'll do my subtraction. -7 minus -3 over -4 minus -2. That gives me -4 over -2, which is just plain old 2. So when I go to make my equation, I have y equals 2x. I'm going to make it an f of x, by the way. And then how do I get y-intercept? Well, you can do some work for it, but if you noticed, if you have 0 here, that is your y-intercept. So it's +1 right here. But we write it as y equals 2x plus 1. We turn it into y equals f of x equals 2x plus 1. So you do have to know how to create the rule from a lot of different ways. You can even create words from rules from words. and any equation, every formula that was ever invented. How about a squared plus b squared equals c squared? This, however, is not a function, but someone created this rule. Someone created that formula. So from somewhere, just like you created this from here, right? So someone created it from somewhere. Okay, the next one is words. I think it's our last one too. This is a very easy one. And the reason these are all easy is because we're just working with linear right now. That's why this should be all a review from Algebra 1, because Algebra 1 was a real linear class, meaning linear, everything was to the first power, to the first power, to the first power, and then when you went to graph it, a linear graphed a line. Towards the end of Algebra 1, you were graphing parabolas. That was no longer linear, that was quadratic. So we're going to work with linear functions. I might draw you a quadratic one, but who cares if I do the drawing of it? But don't forget, you can also make equations for mapping diagrams. Okay, let's take the words, turn it into an equation, turn it into a table. Maybe you could turn it into a graph. I don't even want to do that because now we're getting, it would be really too much because you guys have graphed before, you're fine. So you go to the Big E. This is about the time for the Big E would have ended. I think it ends at the end of September, but we did not have it this year. And the cost is $10 per car and each additional car plus each additional, sorry, we'll just say $10 for the car, not per, because that's a little misleading. So $10 to park the car, $4.50 per person. I do know the Big E costs more than that, by the way. C for the total cost, P for the number of people in the car. So remember, these are the words, right? Right here. Or these are the words. Now let's turn the words into an equation. And then we'll turn the equation into a table. So we're just going back and forth with all these. Some are harder to do than others. So C equals the initial cost of parking the car, then $4.50 per person. So if one person went to the Big E and they had nobody to go with, it would be $14.50. And I got it by doing 10 plus $4.50 times one person. So if a second person went, it would be C equals 10 plus $4.50 times 2, which is $19. 3 would be so on and so forth. And I think until you get to the biggest car, I'm not sure you can even fit 9 in a car. By then, this does not hold any longer as an equation because you're getting out of a domain of the $10 parking. Because if you had to go higher, like up to a van or something, they'd probably charge parking more than $10. So this probably just fits a certain range, well, which is not the right word, but a range for your domain, we'll say. All right, so still moving along. Remember, we're taking notes for 2 sections now. Well, it's really 1 section in the book. And I'm changing the homework that you see at the bottom over here. And anyway, let's keep going. Now I'm going to keep talking about the way you see a function. We usually see functions. You guys are used to seeing y equals 2x plus 3. But now we're going to replace the y with this, f of x. It's just a fancy schmancy way of writing the y. So f of x is not f times x. It gives you, what it does is it gives you more flexibility and more information when you're graphing a lot of other things on the same graph. So when you evaluate a function, believe it or not, it's as easy as being a very good, what's my word? Plugger inner, that's right. So if I call that one function f, and I call that one function g, could you evaluate each of these? It's quite easy. F of 0 goes to the f function and becomes 2 times 0 minus 1, which is 0 minus 1, which is negative 1. This, when you take your quiz, I have people writing as their answer, they write f of negative 1 as their answer. That is not correct. Their answer is plain old negative 1 evaluated. Now, if I ever wanted to graph this function, I would make a table like this and call it x and f of x. And I've already have one of my values. One of my values is I inputted up 0 and output of negative 1 occurred. And I'll show you another one if I like were to input, say, f of 5, just for fun. I would do 2 times 5 plus 3. No, 2 times 5 minus 1. And I would get 10 minus 1, which is 9. So then you'd get 5, 9. So eventually you could make a table out of all your inputs and outputs. So if you wanted to do g of negative 2, you would now go to your g function. And you would do negative 2 squared plus 1. And if you punch this into your calculator as just, I don't know if you can actually see this, but if you punch negative 2 like this and then you square it, you will actually get a negative 4, and that's wrong. So you have to wrap parentheses around the negative 2 and then square it, and you get positive 4. So this would be 4 plus 1, and the answer is 5. So that's what I put here. Answer is 5. So if you guys, well, I'm not going to let you try these on your own because these are really the easy ones. This is something you should have done in Algebra 1. You should have done this in Algebra 1 also. Actually, all of this should have done in Algebra 1, but I'm going to move on forward with the harder ones. Finding f of a. F of a is just plugging in the a for the letter x. And it probably won't give you a nice, easy number. It'll give you a value, not a value, sorry. It'll give you just another expression called 2a plus 1. Is it minus 1? Sorry. And there's your answer there. Okay. Now, f of g of 2, 1 is embedded in the other one, so you have to do the inner one first and find g of 2. So when I find g of 2, I get 2 squared plus 1, which is 4, plus 1, which is 5. So now I have g of 2, which is 5. Now I'd like to find f of g of 2. So what I was doing, and I usually don't write this, but I have to write this for people who don't get what I'm doing. F of g of 2 means I've got to now find out what the g of 2 is and put it in here. There's the g of 2. It's 5. See? So now I'm finding f of 5, which is 2 times 5 minus 1. Final answer is 9. When you give an answer, you do not give 2 answers to me. You just give me that final answer of 9. If you think you know how to do it for the g of f of 2, which will come out differently, you could turn off your screen at any time, try it, and come back to do any of these right here. Go ahead. Okay, hopefully you're back. And run this one, we're going to do f of 2, which is 2 times 2 minus 1, which is 4 minus 1, which is 3. Now I'm going to find g of 3. So that becomes 3 squared plus 1, which is 9 plus 1, which is 10. That's your final answer. On this one, I should have put these two next to each other, but they're actually quite different. See, this one here is saying, here's a number 1. I want you to do 1 over g of 3. So you find what g of 3 is. Let me do it on the side. G of 3 is 3 squared plus 1, 9 plus 1, that's 10. Now I just want 1 over the g of 3. So 1 over 10, done. Now over here, this is asking you for f of 1 over g of 3. So really, I know what 1 over g of 3 is. It's 1 over 10. So it's f of 1 over 10. So you go over here, and now you go to your f thing, and your f function, and you do 2 times 1/10 minus 1, which is 1/5 minus 1, negative 4/5. And you know how we were also putting variables in there? Well, maybe we'll put a binomial variable with a variable in there. So f of a plus, I'll add this one to your squares because I always add something to the squares. So f of a plus 1 becomes 2 times a plus 1 plus 3, 2a plus 2 plus 3, which is 2a plus 5. So kind of ignore this homework. I'm going to put it together with your other homework, but I'm not done yet with my notes. So this right here, we're going to do it. I was going to put it over here, but now we're going to You could do it over here, but I'm making the homework different. So wherever you want to do the homework that I give you, there's plenty of blank paper to do the homework on. But that's not the homework. So we're still taking notes. What was normally day 2 of notes is pushed into day 1 of notes. So pretty much everything I said is just written out over here for you. It's really nice. Like, you're like, oh, I wish I had a place to write all that down. I wrote it for you. A relation. A relation is just a relationship between information. Anything is a relationship. By the way, I wonder why that Yankee symbol's there. You think it's because I like the Yankees? I'll tell you about that in just a second. A relation is just a relationship between the sets of information. Anything can be a relation. However, a function, that's more specific, is a rule that establishes a relationship between the two quantities. The two quantities is the input and the output. What's very important is that for each input there is, circle this word, exactly one output. More than one input can have the same output. Generally, the input is the independent variable and represented by the letter X, and the output is the dependent variable represented by Y. But in this case, we're not going to represent it by Y, we're going to represent it by f of X. Now, there is the New York Yankee symbol there. Best team ever. Best team ever. You should write that down. If these are not on your notes, I could give you points off. Who knows? Best team ever. There we go. Now, here's why I put that symbol there. I didn't do that to upset the Red Sox fans. I did it to show you that when you see f of X, people want to break that apart. If you break it apart, it means something different. Right now, f of X is just a fancy way of saying Y. But if you break that apart, f and X, people could think it's times, and it's not times. It might be times in another place that a teacher says it's times, but not when it's glued together like that. It means the function f of X, which could be Y. If you unglued the Yankee symbol like this, just unglue it. What does that stand for? That stands for New York State. The state of New York, which if I were to draw it, I'm not pretty good at drawing this, but the state of New York. There's Upper New York, there's Greenwich Village, there's Connecticut coming out of it right there, but there's Long Island. But this right here is your state of New York, right? So if you took the N and the Y apart, it would mean something different. If you put the N and the Y back together, it means the team, the New York Yankees. So it's very important that you don't break apart the F and the X, because it will mean something totally different. So f of X right now means X is the input and the output Y is called f of X. One way to describe it is to make it like this input-output table right here. And the table lists the inputs and the outputs, which can also be ordered pairs. So now I'm thinking, aren't I naming all the ways to represent a function? Remember there were 7? Input-output table, ordered pairs. The collection of all of them is the domain. The function collection is all is the range. Here's right here also an input-output table going vertically, right? Let's see. Here's an ordered, doing it in ordered pairs, listing them like this. That's another thing. This is a mapping diagram, and this is a scatter plot. So these are all different ways that we represent our functions, all different ways. This is a horrible picture because these are coming out horribly. But I am going to show you something. This is the graph right over here, 0, 3, right there, 1, 1, right there, 3, 1, right here, 4, 2, right there, and 5, 5. And it really was supposed to be this one right here, 3, 1, if it didn't come out so bad. That's what it was supposed to be. So if you want to know if this is a function, let's look at all of them. See if the input-output table. Yep, 0 has 1, 1 has 1, 3 has one of them, 4 has one of them, and 5 has one of them. Or you could do the vertical line test. Yep, it's a function. So I can say everything on this page is a function. but it was represented in different ways. This was one way it was represented. This was another way it was represented. Here was a third way it was represented. Here was a fourth way it was represented. This all represents the exact same function, which is a function because of the one-to-one thing here, because of the vertical line test here, and in the scatter plot. All right, this was just a little review of what you had to do. It's just a little harder, but not much harder. I'll tell you which pages to upload to, so don't worry. This is just not necessarily notes. I don't think you have to upload this, but if you're looking for things that are a function, this is a function. But if you look at this one, a lot of people think it's not a function because but I put that there. I would never say, hey, I bet I fooled ya. That's just from the internet. But this one is, yes, it is a function because the input of -3 has one output. The input of -2 has one output. A lot of people think this one's not a function, but it is. This one over here is not a function. I don't think you have to upload that page. Okay, this one again, more with functions on non-functions, doing the vertical line test over here. To those 2 points means it's not a function. There's the spaghetti right over here. So you could notice the vertical line test helps tell us this is not a function. Over here, this one is a function. This one's not a function. I don't think you need to upload those pages. There's nothing special to do there. I'll tell you which pages you must upload. This is obviously a page you're going to have to upload. Okay, so section 3.8, still 3.8, which we're going to look at domain and range. Domain and range. Really domain more than range. Sometimes a function is defined by an equation its domain may not be obvious. We'll say obvious looking. So you have to know what the domain is of a function. Remember when I said the domain is the set? The domain of a function is the set. Domain of a function is the set of all the input numbers. Well, it's all the real numbers. Sometimes you don't see them listed. For which the equation has an output. So you might think, well, doesn't the equation always have an output when I put something in? And I'll tell you an example where one doesn't. So say this is my equation I'm thinking of. Y equals x 5 over x minus 3. And if I were to make a table out of this, some easy numbers like, what if I put in 8? Okay, plug in 8. It'll be 5 over 8 minus 3. So it would be 1. And if I put in -2, this would be -1. So it looks like it has a ton of input values, and it does. It has an infinite amount, but one of them doesn't work. What would happen if I plugged in 3 to this? I would get 5 over 3 minus 3, 5 over 0. That can't exist. So 3 is not part of that domain. So I would write that as, I really, back in the day, would write all real numbers, not 3. But there's a way that I write it now, and I'll show you on the next page. So remember, if you're looking to state the domain, try to remember that the denominator cannot equal 0. Another thing that stops you from inputting a number is you can't have a negative number under a square root symbol. You can have it under a cube root, but you can't have it under a square root. So if you take the square root of -25, you'll get an error on your calculator. And the other condition is word problems where you just use your common sense. And I know that's hard to use common sense because you want Miss Golly to tell you what's not part of the domain. And I can tell you actually over here, when we were doing that thing with the car, like parking the car at the big Y, not big Y, big E. And I was saying to you, you got to stop the car at 8 or 9. I mean, maybe some cars fit a 9, but you got to go to a van at 10. So the domain of this stops at 8. So that's the common sense that I'm talking about for a word problem. So you're probably thinking, well, what is this all about? Why are we listing these 3 things? Remember these 3 things. You can flip back to your paper. When I'm going to do all that work here for this, you can flip right back to this and say, what is the condition for not having something in the domain? So let's go to the ones with the denominators right now. So for instance, look at this over here. What would not allow me to plug a number in? I could plug in any number I want, but when I plug it in, what would give me a 0 in the denominator? And if it's not obvious to you, you take the x minus 5 and you say that whole thing cannot equal 0. You add 5 to both of it and you say x cannot equal 5, right? So I don't say x can't equal 5. My answer is really this. All real numbers work. So how do you write all real numbers? You usually write the interval notation negative infinity to infinity. But in this case, you write negative infinity to